On behalf of the Indian Academy of Sciences, I have great pleasure in welcoming you all to the 28th mid-year meeting of the Academy.
I'll start with a few examples. If we take the case of an artificial pacemaker, there is a non-trivial amount of computation and a non-trivial amount of intelligence that goes into it. For example, if you start running or doing some exercise, then you will need more oxygen, and therefore your heart needs to beat faster, and the pacemaker should be able to sense that and step up the rate of your heartbeat so that you can do that kind of an exercise. If you look at the way software controls the temperature in an atomic reactor today, so there are several cooling rods which have to be inserted to bring down the temperature of the reactor and then again taken out so that the temperature of the reactor does not fall below a point. What actually happens is that there are points of no return. If you bring down the temperature beyond a point, then the reactor will shut down. If you raise it above a point, then no matter how many cooling rods you put in, the reactor will go to meltdown. So that software has to be very sensitive to what is happening inside the reactor and accordingly control the rods. If you look at train control systems, for example, these are also software driven. India has started deploying the latest electronic interlocking systems all across the country, and these are equipment which are software driven and control all the signals and the point positions in the railway tracks. In the metro rails, we will increasingly have driverless systems. Already Hyderabad Metro and the new extension of Kolkata Metro will have drivers, but they will not actually be driving the train. Indian Railways is planning to deploy a kind of system called train collision avoidance system, where if a driver jumps a signal, then the train will automatically brake. So these are all software controlled systems, and the area where we have probably the maximum amount of infusion of software and electronics is the modern automobile. So to give you an understanding of how these kinds of systems, which are called cyber physical systems, work, let me take the example of a system which many of your cars have today called the anti-lock braking system. So suppose your car is running at some speed and you hit the brakes, and suppose, let's say, that the brake shoe, it locks itself with the wheel and brings down the angular velocity of the wheel. Will the car stop? Actually no, because if you lock the wheels, two things will happen. The car will start skidding because the translational velocity will still not be contained by the brakes that you apply on the wheels. And the other problem that will happen is you will lose steering capability because your wheels are locked. So even if you tilt the wheels in any direction, the skidding will just take the vehicle in the same direction. So what anti-lock braking system does is it has a processor inside. It will sense the angular velocity using a Hall sensor. It will sense the translational velocity using an accelerometer, and then it will compute what is called a slip ratio. The slip ratio is the ratio between these two velocities, and if that climbs above a value, it will release the brake. So the brake will be applied in a pulsating manner, and the frequency of those pulses will be determined by the amount of brake pedal pressure that you have applied and the slip ratio that it will monitor continuously. What happens because of this kind of infusion of software and electronics into everything that we have today is the problem of safety. How do we guarantee that systems which are controlled by these things are going to operate safely under all conditions? Previously, when we had only electromechanical systems, we would test them under various boundary conditions and then know that, well, it's going to work for all of these. But here there is a software which may do unpredictable things under certain inputs. So if you don't know whether the software is correct, even with all the testing that you do, you will not know whether your system is safe or not. So that is the challenge. So there is an arsenal of new type of methods which are coming into practice today. These are called formal methods, where the system that we want to validate is modeled and there is a formal specification which defines what is correct. And then there are algorithmic platforms, verification methods, computational primarily, which will examine the formal specification and prove that for every run of the model, the properties that you specify here are going to hold. If you find an error, you can go back and revise the design, and this is all happening in a CAD framework. And every control system today, ranging from power systems to systems that are used in automobiles or avionic control systems, they are all modeled and validated in a computational framework first before you actually translate them into the platform where they will run. So in terms of the scope of using formal methods, we are not limited by existing practice. The system model, of course, can be pretty complicated because we can have discrete systems like electronic digital circuits. We can have control systems which control real valued variables. We can have also combinations of those, and therefore there are different types of modeling paradigms which have come up where you can model systems and then validate them. And we are not alone. There are more than 70 top scientists who work in NASA Langley Formal Methods Group, Intel, IBM, Google, Microsoft, General Motors. They have dedicated groups on formal methods because this is turning out to be something which is very useful in practice. But there is also a cartoon in the NASA Langley research group page which says that selling formal methods is probably compared to be as difficult as selling electric eels in a fish market. The reason is that very few people will really understand that whether we can take a real world system and how do we model it in a system model, and then how do we write a formal specification and how do we validate it. So it requires a special skill set, and you need to understand the physics of the actual system, you need to understand the mathematics of the modeling paradigms, and you need to have the algorithms and the programming ability to finally prove that the system is correct. So in my research group, we have combinations of electrical engineers, mechanical engineers, computer scientists, and mathematicians. Several international safety standards have recommended the use of formal methods in verification, and a few of these are there. So from an Indian perspective, today these safety standards, they only recommend the use of formal methods, they don't make it mandatory. But it is anticipated that in future that will happen. So some of our certification agencies like CENILAC for DRDO, they need to get into the art of formally validating systems so that we can actually remain competitive in the international market. So let me give a brief overview about how the technology actually works. So there are various types of artifacts for specifying the safety of a particular system. The traditional things which we used to use in AI planning and also in several deduction frameworks which existed in computer science for more than half a century now, they are essentially around the Boolean logic. But there are also newer extensions like temporal logic which can express properties over time. So you can say that if a bus request has come, then within one clock cycle, if the bus grant does not come, then within one cycle, if the bus grant does not come, then that is an error, which says that the bus grant should come within the next 2 cycles from which the bus request was made. And you can have real valued extensions of these languages, and these are areas where extensively logicians and mathematicians are working together. There are language standards which are industry language standards which leverage these logics and are already there in industrial practice. For example, system Verilog assertions is used by every chip design company today to express the correctness requirements of an integrated circuit. To represent the state spaces, one important thing that we have to understand is that for most of these real world systems, the state space size is enormous. So if we start enumerating each state, we cannot do that. For example, if you look at the number of states that a modern Intel processor has, that is more than the number of atoms in the universe. So therefore, there is no question of really trying to explore all the states. Therefore, these methods have to work on symbolic representations of states, and there are tools and technologies for doing that, and that is a kind of science which is developing. How do we explore huge state spaces without enumerating them? And to give you an example about what I mean here, that if you take for example the way that we had traditionally been verifying electronic systems through simulation. So what does simulation do? We start from any of the initial states of the system, and then we provide inputs, simulate the system, we go to a next state, and we keep on visiting next states, and that in its entirety is a simulation run. Now a simulation run only tells you the behavior for one particular combination of inputs. It does not tell you whether there is another path which can lead you to the bad states. And then if you started to explore all possible paths to the bad states one by one, then we would be confronting with that state space explosion, which is, as I said, more than the number of atoms of the universe. So what we therefore needs to do is not to simulate, but work mathematically by expanding the set of initial states, finding out mathematically what are the next set of states, and keep on doing this so that we go from set of states to set of states, and we work not in the state space but in the formula space. So I mean, it's a full-length semester course to really define what I'm talking about here, but broadly that is the intent that and the idea that formal methods try to do. So let me look at the present state of the art here. So there are a lot of tools which are already there, some of them commercial. For example, in the electronics domain, for verification of digital integrated circuits, there are several commercial tools which are available from the top EDA companies. In the network domain, there are no commercial tools. In the software domain, there are excellent public domain tools developed by some of the top universities. For example, CBMC has been used to verify more than 300 different systems all across the world. This is a tool which is developed and maintained by Oxford. And then we have also in the control domain several offerings which are available. So that gives us the ability to really target different tools to different types of applications. This is a snapshot of the type of work that my group does. So we work on verification problems in integrated circuits on railway signaling, automotive control, avionics software, smart power grids, and also network access control. And we have been very privileged to work with some of the top companies in these areas, and many of my students have been fully funded by these industry sponsored projects. I will skip through this. This is a summary of the different technical contributions that were made, but in the best interest of time, I will talk about recent work that we have done with Indian Railways. We are very proud that Indian Railways has started using this thing to some extent as of now, and they have also funded a big center on formal methods at IIT Kharagpur. So I will explain the way that the signaling system works. So the signaling system, it's basically a computer which controls two things. One are the signals, the red, yellow and green signals that we are familiar with, and the other are the point settings. As you know that when the train has to move either this way or that way, there are certain parts in the in the railway line which moves from one to another side, right? I mean, those of you who have watched old Hindi films, you will see that in the climax situation, someone gets stuck there, and then there is a lot of issue at that time. So those are the point settings. Those are actually controlled through relays by the EI equipment, the electronic interlocking equipment. And equipment can actually sense the presence of the train using what are called track circuits. And there are many different types of track circuits, including ones which can count the number of wheels which has passed over it and so on and so forth. Right? And then there is the station master, which when a train is approaching the yard, it tries to determine where my train should go. Right? Now the present life cycle of developing the signaling logic in Indian railways is as follows, and that is similar to what happens in every railway in the world, that you start with a yard layout, that is the graphical description of the signals and the routes through which trains can pass, from which a control table, a table which is generated manually, which tells you that which routes are conflicting with which routes. If the station master gives access to this route, those routes should automatically get locked. And then from that, there is a logic which is developed again manually, and that logic is fed into the equipment, and the equipment runs a software to interpret the logic. That software comes with very rigorous testing, the rigorous certification requirements, and is certified by 4 or 5 vendors across the world. But the application logic which goes into it, there is no guarantee that that is correct. And it has been in the last 5-6 years observed that in yards in UK and Australia, there were errors in the application logic which went into this. It went through the entire factory acceptance test, but it was not detected until a specific combination of train movements happened. So that is a scary thing. So it may not happen for many years, then suddenly on some day that combination of train movements can lead to a signal failure. So the important thing is to make sure that this application logic is formally proven to be correct. If there are errors here during the test, railways has to go back and redefine the application logic, and of course they have to pay for each loop because this testing is done by a third party. And then finally it is deployed. Then for every upgradation we go through the whole loop again. So this is what we did for them. So we built a tool which can automatically generate the control table, and from the control table it can generate these formal properties which are based on the international railway signaling principles, and they can be validated on the application logic which is designed by the railways. And then there is this back-end model checker or the formal prover which proves whether that logic is correct, and if it is not, then it immediately shows a counterexample. So this can help. Finally, if you can prove that all the properties hold on your application logic, then you are done. And you know that no matter what movement of train happens, your logic is safe. I will skip this in the best interest of time. Semiconductor area is an area where we have extensively worked on various problems, right from the architecture level to the RTL level down to the transistor level. And this kind of chronologically captures the various things we have done with various companies. We are working on automotive ECS, where we have very ambitious plans within my group as well as in the institute. We are validating a real-time operating system. The first real-time operating system from India was developed by HAL very recently. We are doing the formal validation of that. We also work with the National Power Grid Corporation on validating vulnerabilities in power grids. This is a kind of flagship project called AutoSafe, which we have done in the past. And FMSafe is a formal method center which has been set up under the imprint scheme of MHRD in partnership with experts on formal methods in IIT Bombay and IIT Kanpur. And I would like to conclude with a picture of a unique thing that happens in IIT Kharagpur. This is the illumination, a picture of the illumination. As you can see that this picture is actually composed by earthen diyas, and the students, a battery of something like 500 students work together to put diyas in a grid and build this picture, and they are all oil-filled diyas, no electronic or there is no electric thing here. And that diyas, all those diyas have to be lit up within a period of 30 seconds to give you this view. Okay, thank you.
Theory of perfect invariance developed for this. What is that? Can you elaborate?
Okay. To give you a broad idea, what an invariant means is that a property which holds always, right? Now, a lot of properties can be, so if there is a property which fails, then that may happen through a sequence of visiting several states, right? Now, what a perfect invariant says is that it is, if you are in a safe state, then if you can prove that the next state is also safe, right? That can be validated by looking at the transition function only, because I need to prove over one step that if I am in a safe state, then the next state is safe, right? Additionally, if you can show that your initial state of the system is safe, then inductively you have shown that everything is safe, right? Now, the key to writing a formal property in this form is basically the theory of perfect invariance. And most of the properties in railway signaling can be expressed as perfect invariance.
I'm just curious if the application logic which right now the railways is providing, can it also not be automatically generated given the structure of the layout of the tracks, then, and we want to avoid accident?
Yes, so that's a very good question, and the answer is yes, it can be. But what happens is when you have a big yard, then this logic is not cannot be put in one machine. So it's actually a distributed system with several electronic interlocking equipment. Like for example, Kharagpur is going for an upgradation. They will have 4 of these. Howrah station I think has around 6 of these. So the entire logic will be partitioned into those, and there is also a handshaking that happens between them. Automatically synthesizing that is a bit tricky right now. But that is there in the scheme of things. Yes.
What does the institute do to light all those lamps in 30 seconds?
What does the institute do? So this is a student-driven initiative. So you have, so this is a competition. Each of the student hostels, they participate in this competition, and there is a schedule in which the judges arrive. So when they know that the judges are on their way, then they have this structure which is built in which 500 students will parallelly light it. So it's parallel.